This is Dr. Mimi Lam from Case Western Reserve University Medical School, and in this video called Basic Renal and Dialysis Physiology Part 1, I would like to help you understand at a very basic level how the kidney works and to start you thinking about the ways in which a kidney and a dialysis machine are different. In this video, we will cover two things: the process of glomerular filtration and the concept and calculation of clearance. Let's begin with some very basic glomerular hemodynamics. Within each tiny unit or nephron, of which there are about 2 million in our two kidneys, we can see how glomerular filtrate is formed. Blood enters the afferent arterioles at the rate of about 1,000 to 1,200 mL per minute for all the nephrons combined. Plasma makes up a little over half of blood volume, so renal plasma flow rate is about 600 to 700 mL per minute. Then there's a portion of the plasma that gets filtered through the fenestrated glomerular capillaries and enters the proximal tubule. The reason this filtration happens for plasma only is that blood has the rest of the stuff in it that's too big to pass through the holes of the capillaries, stuff like blood cells and large protein molecules. This portion is known as the filtration fraction and is normally about 0.20. In other words, about 20% of renal plasma flow of 600 mL per minute becomes glomerular filtrate, while the other 80% passes right on through the glomerulus and exits out the efferent arteriole. The rate at which this filtrate is formed by all the nephrons working together, about 20% of renal plasma flow rate, is called glomerular filtration rate and is about 120 mL per minute. So in total, about 1,000 mL of blood, which would be 600 of plasma, enter the 2 million nephrons each minute, and about 120 mL, or 20% of the plasma portion, becomes glomerular filtrate that begins its journey down the nephron, where it will gradually be transformed from plasma into urine. So now you see how things are supposed to work in a single nephron and how to estimate what GFR is supposed to be. But the question we're really interested in is, what is the GFR in the whole kidney and how can we measure it? Keep in mind that the hemodynamics are not the same in all nephrons. You have 2 million nephrons working simultaneously. They come in slightly different sizes, lengths, and levels of efficiency, and some may be damaged by age or diseases such as diabetes or hypertension. All of these factors can affect the incoming renal plasma flow for a given nephron and determine what percent of plasma is going to get filtered through the glomerular capillaries to contribute to the total glomerular filtrate. So how do we know the real GFR of an actual person's kidneys? Before we try to answer that question, we need to first understand the concept of clearance. The definition of clearance is the volume of plasma per unit of time, usually in mLs per minute, from which a substance has been completely removed by the kidneys and excreted in the urine. Say you have a toxin called X in your body and your kidneys are supposed to be getting rid of it. Each of the 2 million nephrons is working away, extracting molecules of X from the plasma and putting them in the urine, and you want to have a measure of how well your kidneys are doing at this process. This is the formula that we use. Clearance of X equals the urine concentration of X multiplied by the urine flow rate divided by the plasma concentration of X. So we just refer to this part as UV over P. As we go over this idea of clearance, we'll plug in some numbers so you can see how it works. First, we measure the rate at which X is excreted in the urine by multiplying the urine concentration of X, in this example 10 milligrams per ml, by the urine flow rate, 2 mLs per minute. So 20 milligrams of X, 10 times 2, are being excreted in the urine each minute. We know that the plasma concentration of X is 4 milligrams per ml, so when you see 20 milligrams of X appear in the urine, you know that the kidney had to completely extract X from 20 divided by 4, or 5 mLs of plasma, to make that happen. So the clearance of X is 5 mLs per minute. meaning that 2 million nephrons, each extracting X from microdrops of plasma, amounts to a total of 5 mLs of plasma being completely cleared of X every minute. As you can see, this simple formula of UV over P allows you to determine the clearing ability for the kidney as a whole without having to think about the fact that not all nephrons work the same, not all of them clear X at the same rate, but the kidney as a whole clears it at this rate. Well, after all that, it turns out that we don't actually care about clearance in itself. We only care because it allows us to determine GFR, and here's how that works. Luckily for us, there is a substance called inulin, which is the product of a plant called the Jerusalem artichoke, and don't ask me how they discovered this, but inulin is a relatively small molecule, molecular weight 5,200, that is not protein bound, so it's freely filtered at the glomerulus and is not secreted, reabsorbed, or metabolized by tubular cells. So what this means is that the amount of inulin filtered in milligrams per minute is going to equal the amount that comes out in the urine in milligrams per minute, because whatever gets filtered is what you end up with. No inulin is added, removed, or metabolized by the tubules. So knowing that, you can now set up an equation that says the amount of inulin filtered equals the amount excreted, and you can calculate the two parts. The amount filtered is going to be the plasma concentration of inulin multiplied by the rate at which plasma is filtered, or the GFR, and the amount excreted is going to be the urine concentration of inulin multiplied by the urine flow rate. And so now you have an equation where you can measure 3 of the variables, and you can calculate the unknown, which is the GFR, which is what you're really interested in. Notice that the GFR in the rearranged equation equals UV over P, our old friend, the formula for clearance. So at least for inulin, if you can calculate the UV over P clearance, you've got your GFR. Now, this is a quick visual to help you understand how it is that inulin clearance equals GFR. You start with a volume of plasma that contains molecules of inulin. This gets filtered by the glomeruli to make glomerular filtrate. And from there, almost all of the water is reabsorbed and returned to the circulation. This has to happen because the rate at which glomerular filtrate is formed is so high, like 120 mLs per minute or upwards of 150 liters per day, that you wouldn't want to be losing all this volume in the urine, so you simply reabsorb the water and return it to the plasma volume while leaving the inulin molecules in the filtrate where they can later be excreted in the urine. Notice that every time you filter molecules of inulin, they end up in the urine while plasma volume doesn't change. And the total amount filtered in milligrams per minute is going to equal the total amount excreted in milligrams per minute. So what this means is that the volume of plasma filtered per minute, in other words, the GFR, equals the volume per minute from which all inulin has been removed, which, remember, is the definition of inulin clearance. And so the simple UV over P calculation of inulin clearance gives you the GFR. Note again that this is a very special situation in which clearance equals GFR, but only because the characteristics of inulin mean that every molecule of inulin that is filtered ends up in the urine, so that you can back calculate to find how many mLs of plasma had to be filtered and cleared in order to end up with that amount in the urine. So because of inulin's special characteristics, we can use its clearance, UV over P, to calculate GFR. This is not as easy as it may sound, because in order to calculate the GFR, you first have to start an IV infusion of inulin into the patient and continue it until the plasma concentration of inulin is constant at a steady state. Then you can measure the 3 variables and calculate the GFR quite accurately, but it's a pain to do this. So luckily for us, there is an endogenous substance called creatinine that can give us approximately the same information without the hassle of an IV infusion and waiting for things to reach a steady state. Because creatinine is a muscle breakdown product, it already exists in our bodies, and under normal circumstances, it's already present at a steady state concentration in the blood. Like inulin, it's freely filtered and minimally altered during its trip from the glomerulus all the way down the nephron. So all we have to do is to calculate creatinine clearance using our UV/P formula, and the number will closely approximate GFR. There are some minor reasons that creatinine clearance is not quite as accurate an estimate of GFR as inulin clearance is, but overall, despite some inaccuracies that tend to cancel each other out, it turns out that creatinine clearance is actually a very good approximation of GFR at normal levels of renal function. However, keep in mind that even though this is easier than doing an inulin clearance procedure, you do have to calculate the urine flow rate, or VDOT, by collecting a timed urine, usually for 24 hours, and then measuring the volume of urine and concentrations of creatinine in the plasma and in the urine in order to do the calculation. So now you can understand how the concept of clearance came about and how basic renal physiology was elegantly used to calculate GFR. Thank goodness in this day and age, there are less cumbersome methods, even though we still do sometimes collect 24-hour urines for the calculation of creatinine clearance. But these days, the most accurate way to determine GFR is through a radiotracer like iothalamate that's handled like inulin. But its rate of filtration and excretion can be tracked by measuring radioactivity over the kidney and the rate at which it decreases as urine is made and excreted, instead of having to do multiple chemical analyses. On the other hand, for clinical studies and taking care of patients, we need something that is easy to do, doesn't take much time, and is inexpensive. And so we use the eGFR, or estimated GFR. This is calculated from demographic equations that are derived from multivariate analysis of large populations, and the eGFR is based on variables such as gender, age, serum creatinine, and body weight. So this is what we use for taking care of patients and for doing large clinical studies. So before we conclude, I want to remind you that nephrons don't just filter plasma and allow it to flow through the tubules and go out in the urine. They have two more things that they can do to the glomerular filtrate. So here is part of a renal tubule with a lumen and lined by renal tubular cells and surrounded by capillaries. So the filtrate comes through the glomerular capillaries, enters the tubules, contains a lot of sodium and water, as well as things like urea and creatinine and metabolic waste products or toxins that you want to get rid of. Once inside the lumen, these things can be reabsorbed by the tubular cells and returned to the circulation through these surrounding capillaries. So what is reabsorbed is mainly large amounts of sodium and water, and also things that you don't want to lose, like bicarbonate and glucose, and those are returned to the circulation instead of being excreted in the urine. On the other hand, you can also take things from the capillaries, from the blood, and pick them up with tubular cells and secrete them into the lumen to augment excretion of certain substances, such as potassium and hydrogen ion, and even exogenous substances like penicillin. So basically what these nephrons are doing is filtering huge amounts of plasma at 120 mLs per minute, 24/7, no rests or holidays, and allowing toxins and metabolic waste products to be excreted in the urine while reclaiming or reabsorbing stuff that you don't want to lose in the urine and returning it to the circulation, and augmenting the amounts of stuff you really need to get rid of by secreting it from the capillaries. And as a result, what you see coming out in the urine is the result of plasma undergoing filtration, reabsorption, and secretion. So I would like to leave you with the thought that the kidneys can do some amazing things and can alter the composition of filtrate and therefore of a person's blood by quite a bit by their processes of reabsorption from the tubules into the circulation and secretion from circulation into the tubules. This is something that dialysis filters, which are basically inert capillaries, cannot do nearly as well. And the way that the process of dialysis alters blood composition and gets rid of toxins and wastes is another whole topic that will be covered in a later video. So thank you for listening, and if you have questions or corrections or comments, please feel free to email them to me at mlam@metrohealth.org.